All right, here we go. So we left off right here at 4.5. We were talking about, of course, I've lost my 4.5 paper. Here it is. Okay, so we were talking about joint probability, right? Where you see the word and. What's the probability of this and this happening? So that's what we had kind of covered up here at the top, was that situation. It made it look really complicated and crazy. It's not. Once we go through and do the examples, it's actually really easy. Now we're going to talk about unions of events. So this is the word or. Instead of having the probability of this and this happening, we're now going to look at the probability of this or this happening. Okay, so it's a little different. You got to really look in there at the words. Okay, so what's the difference? Well, the difference is now we're looking at all the outcomes of event A or event B or both. So now it's not just what they have in common, right? With the little Venn diagram, it's like all of A, all of B, or what they have in common, okay? So it could be any of those. So it's a little more complicated because it's more inclusive. So with the or, you actually are going to have to do a little bit more work. Still easy, but a little bit more work, okay? So with joint probability, with the and, you're going to multiply. With the union, you're going to add and then subtract. So it's called the addition rule, okay? So you'll take the marginal probability of the first event, add it to the marginal probability of the second event, and then minus the joint probability of both. Why are we minusing? Because otherwise you're counting some events twice. That's kind of hard to see until we do the examples. And then it's like, oh yeah, okay. So kind of hold off on that. All right, so of course we have times when they are mutually not exclusive. Okay, so we're going to assume this type unless it tells us otherwise. So that's almost like 99% of the time we're dealing with this. So you'll have the probability of event A plus the probability, that's supposed to be a B, of event B minus the probability of event A and B. Okay, and we'll look again why we're subtracting that out in a minute. Okay, all right, what about if we're finding the union of mutually exclusive events? Now it'll state if it's this type, it'll tell you if it's this type, so you'll know. Okay, but in this case, when things are mutually exclusive, that means that the probability of them happening together at the same time is 0, because mutually exclusive events can't happen at the same time. So that means we get to leave off this back part. We don't have to include that. So in that case, it's just going to be the probability of event A plus the probability of event B. Pretty easy. Okay. So let's look at, I know I don't have room in here, but let's just squeeze in a little example right here in this little blank part. Okay. Because this is going to be a Wiley question and I didn't get it typed up as an example. So let's just squeeze one in. What if it tells you to find the probability of, whoops, I put the wrong, A or B, so we know it's a union, and then it gives you that the probability of event A is 0.18, the probability of event B is 0.53, and the probability of event A and B occurring together is 0.6. Okay, so what if it gives you that information for Wiley and it wants you to find the probability of A or B? Well, it didn't tell us that they were mutually exclusive. In fact, we know they're not because this is something other than 0. So we're going to assume it's this type, right? And we're just going to add these two together because that's what it says to do and subtract that one and you have your answer. Okay, so all we're going to do is take 0.18 plus 0.53 minus 0.6. I came up with 0.11, but I have something erased there, so we'll just pretend that's right. Okay, that's it. That's how you would find the probability of a union. There is a question like that on Wiley. Now, most of the time, you're going to have to come up with these decimals. They're going to give you a chart, right? Like a frequency distribution, and you have to come up with those probabilities. But one of the questions in Wiley, and I can't remember if it's the homework or the quiz, they just give you these values. So you just strictly follow this formula. That's all you got to do. Oh, it's number 14 on the homework. Okay, so it's number 14 on your homework. Thank you. I thought that was, you meant here. I thought, good grief, I can't even add. 13 on the homework. Mark that on there. Okay, there's your Wiley 13 homework. Awesome. Okay. All right. Now 4.6 has some fun calculator stuff. Okay, so that's kind of the end of probability stuff. All right, so everybody okay with unions? I know it's very abstract right now. It'll be better when we get some real numbers. But okay, let's talk about counting rule. So the counting rule, there's questions like this on the ACT galore. Okay, so the counting rule just means that if you have a lot of different choices, a lot of possible outcomes, okay, that can result from each step of an experiment, the way that you find the end result is you just multiply them all together. That's it, okay? So multiply together the total number of outcomes from each step. All right, so sometimes, here's a little example down here. So sometimes at like fancy restaurants, especially around Valentine's Day, you can go in and you can pay like a set price. Like maybe it's $49 per person, okay, done, no matter what you get. And they'll give you a little menu. And then they'll give you choices. And on the menu, you can choose one of 4 appetizers. And then you get to choose one of 6 entrees or your main meal, right? You get to choose out of 3 desserts. And then you get like 2 choices to drink, right? So a lot of restaurants will do that for like Valentine's Day or Christmas or different things like that. So if you're at the restaurant and you've paid your little set price and they give you this menu, how many possible different meals could you come up with these choices? Well, you just multiply all your choices together, believe it or not, and that's how many meals you could have. It's that easy. So I'm going to multiply the 4 times the 6 times the 3 times the 2. Turns out there's 144 possible meals you could put together. Easy enough. Okay, that's the counting rule. All right, everybody okay with that? Simple enough. Okay, let's make it a little more complicated. All right, last page before we do some Wiley problems. Okay. So now let's talk about factorial. Some of you are already familiar with factorials probably. It looks like an exclamation point, but it's in math. Okay, so it's not that I'm super excited about 5, yay 5, right? It's that I want you to find the factorial of 5. So the factorial is just the product, so we're multiplying all the integers, whole numbers, from whatever number you have all the way down to 1. Don't include 0, because what happens if you multiply by 0? You get 0, so that's not helpful. Everything would be 0. Okay. So if I want to find 5 factorial, that means I'm going to have 5 times 4 times 3 times 2 times 1. That's what 5 factorial means. Okay, you multiply all those together, you get 120. That's your answer. Okay, easy enough. Now, again, don't include 0, but sometimes you'll have this. And be careful because it's also a Wiley question and it's a test question, okay? What would be 0 factorial? Well, we don't include 0. We're just going to have a 1. Your answer is just 1 for that, okay? All right, so we're going to do a couple of other examples here. Let's do 8 factorial and then let's do like 1 in parentheses factorial. But sometimes this can get really tedious. So that's where your calculator comes in. So everybody get your calculator ready. There's a factorial in there for you. Okay. You're going to go to math and you're going to scooch, scooch, scooch over to PRB. That means probability. And then you're going to see your exclamation point, your factorial. Now you need to enter your number first. That's the only thing. So let me switch over here. Okay. Here we go on the calculator. All right. So here's my math. Scooch, scooch, scooch. Here's my exclamation point, right? But I have to enter my number first. Let's go back to 5 and just make sure that works. So I'll do 5, math, scooch, scooch, scooch. There we go, 120, just like we thought. Easy enough. Okay, what if you're on the test and you can't remember what 0 factorial is? Hey, put in the calculator. There's your 0. Here's your x factorial. You get a 1. So you don't even have to remember that little fun fact. You can put it right in your calculator on test day and make sure it's right. Okay, if we want to do 8 factorial, okay, he's 40,320. Well, that escalated really quickly, right? Because 5 factorial was only 120. And then holy cow, 8 factorial went up fast. Okay, so if you wanted to do it by hand because you just love it, okay, there you go, right? Or it's 40,320. Wow. Okay, you can even do it with numbers in parentheses. Now, we know 15 minus 10 is 5. What's 5 factorial? 120. We already found it. But what if we don't even want to do that. Subtraction's just too much for us, right? You can just put the whole thing in. Scooch, scooch, scooch. Okay. Look, you get your 120. You don't even have to go ahead and subtract first. So that button is really handy, all right, for a lot of reasons. There are a lot of formulas that use factorial. And so in this case, you can just make your calculator do it and it works out well. Okay. All right. That brings us to the next 2 items, which we're going to need math probability to find on our calculator because you do not want to do these by hand. Okay. So first one, combinations. So these are the number of ways you can select a certain number of elements from some choices. Now, this is different from the counting rule. The counting rule, you had a lot of steps, right? You had a lot of this many appetizers, this many entrees, this many desserts. This is just one pool of numbers, and you want to select a certain number out of that one pool. So this is different, okay? So the formula for him, he's a big giant C. On the left, you have a little n. Oh, you can't see. Sorry, guys, you're all looking at me like I'm crazy. I am crazy. Okay, there we go. So you have a big C. On the left is a little n. On the right is a little x. Okay. This is going to equal a fraction. Your numerator is going to be n factorial. All right. Your denominator is x factorial times n minus x factorial. Okay, that's why we did all that factorial practice. Because again, back in the Stone Ages, we had to do all this by hand. Okay, your calculator already has a combination button built in. So you don't even need to know that. You're going to go right to your calculator. Let's talk about it a minute. So n, the number you see first, is the bigger number. Okay. X, the number that's to the right, is the smaller number. If you mix them up and put them in the wrong order, you're going to get the wrong answer. So be really careful about that. Okay. In your calculator, it doesn't say NCX because the calculator doesn't like to use X unless it's graphing. It gets a little funny about it. So in your calculator, it's actually NCR in your calculator. Okay. So the R has been replaced. All right. And so you might have seen him. He's right by the factorial button. You're going to do math, scooch, 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 prob, and there he is. Now, depending on your calculator that you have, some of you with the newer calculators can hit that NCR first and then put the number on each side. If you have the older ones, me, Andrew, Anna, I think the 3 of us, we're going to have to put in the bigger number first. then hit NCR, then hit the smaller. Okay, so let's do an example. All right, let's say you're in an ice cream shop. They have 6 flavors. It's a crappy ice cream shop. Okay, you get 6. All right. How many combinations are possible if you're going to choose 2? You want 2 scoops. How many possible combinations are there? Okay, so 6 is the bigger number and 2 is the smaller. That's what we're trying to find. Okay, if you wanted to do it old school, you would have 6 factorial on the top, 2 factorial times 6 minus 2 factorial on the bottom. Okay, if you were just dying to do it. Otherwise, let's go to our calculator. Okay, so I have the older one, so I'm going to have to put in the bigger number first. Math, go to prob. There's my NCR. He's right above factorial. And then my 2. And I get 15. I have 15 possible combinations of flavors. Okay, so play with that. Make sure you know your calculator. Do you have to put 6 first? Do you have to, can you wait and do NCR first? You know, figure out what your calculator likes. Is everybody okay with it though? All right, let's try one more. How about, all right, how about 11C6? What if there were 11 choices and you wanted 6 of those choices? Okay, just to see what you come up with, I got to put 11 first. Going over here, 6. I get 462. There we go. Okay, and there's my answer. You know what? I'm going to grab that. Okay. This way I don't have to. Okay. So there we go. We get 462. Does that make sense? Got your combinations in there? Okay. Very last thing we're going to look at then. Permutations. Permutations are different. Permutations take it up a notch from combinations. So combinations, let's say we had an ice cream cone, right? We were in the ice cream shop, 6 flavors. We want to know how many possible combinations we can have, you know, using 2 flavors. So that's all they cared about. If I said vanilla chocolate, that was 1 combination. Permutations, they suddenly care about the order. The order of the selection is taken into account. So combinations, vanilla chocolate's 1. Permutation, vanilla chocolate is 2. Because think about it, I could have vanilla on the bottom and chocolate on the top, or chocolate on the bottom and vanilla on the top. Suddenly the order matters for permutation. So that's 2 separate orders. Does that make sense? So suddenly we really, really care about the order. Okay, so he's just like your C, but he's not a C, crying out loud, he's a P. Okay, NPX. All right, so you're still going to have an n factorial on the top, but now you just have n minus x factorial on the bottom. That's a minus x. I know it kind of blended into the line there, n minus x. Okay. All right, so in your calculator, this is NPR. He's right there above NCR. These are much larger. Look at your formulas. What you're missing is that x factorial in the bottom. You're not dividing by as large of a number. So if you're not dividing by as large of a number, your answer is going to be larger. Okay, so he's going to be much bigger. All right, so here we go. You're at an ice cream shop with 20 flavors. How many combinations? It still says combinations. Notice it did. Sometimes it'll say permutations. Super easy to figure out. Sometimes it says combinations are possible. If you choose 3 flavors for your cone, the order is important. That's the key. Now you know it's a permutation. So if they use the P word, fantastic. But they might not. They might say combination, but then they use the phrase, the order is important. and then it's permutation, okay? So you could always do this and find the answer, or, okay, we could take our calculator. All right, I can't remember on mine if I have to put it in first or not. I'm gonna throw it in. Let's see. And then math, probability, there's my NPR. Yeah, I still have to on this guy. Okay, and I get 6,840. Sound good? All right, let's just do one more down here. What if I give you 7P4? 7P4. Okay, so 7 NPR 4, and I get 840. Okay, everybody okay with that? All right, so this one was this. This is 840. Okay, so that's chapter 4. That would be what we came up with. Okay. All right, let's do some examples then. Let's look at Wiley. So remember, these are just a whole lot of homework and quiz questions that I felt were a little tricky. So I thought we better make sure we knew. Let me make sure I'm recording right here. Okay. All right. So this says, suppose you toss a coin twice. Okay, well, we talked about that earlier. But look at this. Now it says draw a tree diagram. What in the heck? We haven't talked about a tree diagram. Okay, from this experiment, label the final outcomes. Well, you know, in Wiley, you're not drawing anything, but you are identifying. So we need to talk about tree diagrams. Tree diagrams are actually really helpful when you get into really complicated statistics problems, because it's like a flow chart. It gives you a little path to follow that really give you numbers. So they're kind of nice, but let's just look at what that looks like. Okay, so we're going to start off here with a little dot. We're going to say this is our first toss. Okay, we flipped our coin right there, first toss. Okay, well, there's two paths we can take, right? We could get a head, or we could get a tail. All right, perfect. Now, if you only flip the coin once, you're done. This is the end of the line for you. But this says we flipped it twice, okay? So that means this is going to be another event. And they usually draw like a dotted line or a straight line to indicate another event took place. So now there's a second toss that took place, okay? So let's say for our first toss, we flipped it, we got a head, all right? Well, maybe for our second toss, we got another head, but we could have also gotten a tail, right? Okay. Maybe the first time we flipped it, we got a tail. Well, then we could have gotten a head the second time, or a tail. That would be the tree diagram. There's nothing else. There's not another event to take place. Now, if you flipped it again, we'd go dot, 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 third toss, and we'd branch that, and we'd branch that, and we'd branch that, and we would branch that, and we would just keep going and going and going, depending on how complicated it was, and you would follow the path that matched your results, okay? So then I think they label these kind of like this, and they want to know, what does every little end dot end up meaning? Okay, well, let's see. In order to get to A, what did you do? You ended up with a head, head. So that's what path A would give you. All right, what would path B give you? It would give you head, tail. Okay. Path C is going to give you tail, head. That's a different outcome, right? And then good old D is going to be tail, tail. That's it. So that's a tree diagram, okay? No big deal. It's just sometimes they like to demonstrate events with it. It's kind of fun. I don't know. Okay. Everyone all right with tree diagrams? Good? Okay. All right, let's look at probabilities. All right, we did one of these on the board together. Let's talk about it. So which of the following cannot be probabilities of an event? Now there's going to be more than one. Let's remember the two rules of probability. The first rule is all probabilities have to be between what two numbers? 0 and 1. And they can include 0 and 1, but between 0 and 1. Okay. And then the second rule of probability that doesn't really apply to this is that they all have to add up to be 1. So we just want to remember our probabilities have to be between 0 and 1, and they can include those. So is this a probability? So I'm going to circle him because he cannot be a probability. Okay, what about 0.97? Sure. 1? Sure. 1/4? Yep. -1/2? No, he's negative. All right, 8/7? No, why isn't he? He's too big, he's greater than 1. Boy, some students are like, I don't know, he's a fraction. No, he's, it's because he's bigger than 1. Okay, what about the negative guy? No. And then what about 0? Good. All right, that's simple. So they're just trying to get you to remember the first rule of probability, everything between 0 and 1, including 0 and 1. Okay. All right, let's do some real deal probabilities then. Here we go. This is shopping and not shopping and yay. Okay, male, female. All right, well, first of all, remember, before we jump into the questions, we need to complete the chart. So we need totals. Always a good idea to get totals. Okay, so let's see. Have shop total. If I add these two together, I get 1,100. Have not, 900. Okay, I'll add a cross for the males. I get 1,000 males. Also get 1,000 females. Okay, this number right here, this grand total number, better be the vertical total and the horizontal total, right? And it's 2,000. Always check and make sure you didn't, mess up a number. It's not off in any way. Everybody okay with those? Okay, let's do some probabilities. So one adult is going to be selected at random from these 2,000. Find the probability that the adult has never shopped on the internet. Well, that's only one little category. So that's a marginal probability. If you wanted to write this over as like not shopped or something, you could. You don't have to, but that might be another way it was presented. Okay. All right. Since it's only asking for one item, he's marginal. That means the grand total is on the bottom. And one of those little marginal items is on the top. So what's going to go on the top for have never shopped? 900. Awesome. Now remember, we like decimals. So this is going to be 0.45. There you go. Okay. Let's look at the probability that the adult is a male. Okay, it's only one little item it wants, only one thing, one category. So we could write it over like this. That would be the same thing. My denominator is the big grand total since it only wants one thing. The numerator is going to be the total of males. Just so happens it's 1,000. That's going to be 0.5. Okay. Maybe I should do 0.50 if we're going to do two decimal places. So both of these were marginal. They had 2,000 on the bottom because they were only asking for one item, right? That's it. Okay, 3 and 4 down here, we got a couple of things happening and I see the G word. Given, okay? I see a given. When you see given, 2,000 is no longer your denominator. These are now inside. These are conditional probabilities. There are two conditions that have to be met. You have to go inside and the grand total is no longer in play. All right, here we go. So trying to make it so you can still see the bottom there. All right, if I wanted to write this over, just in case you see it like this, it would be the probability that they have shopped, given, that's the line, the person is a female, okay? So if you saw that, that's the same thing as that sentence. Now remember, whatever's after the given is the denominator. So in this case, the female total is the denominator. Okay, female total is 1,000. All right, now to find the top, I have to go inside to find the top. Okay, so I'm looking at just the female row because that's the total that I use. So I only have two options. I have shopped for 700, have not shopped for 300. This is have shopped 700. Okay, and you get 0.70. Pretty good. All right, let's try one more of these then. I can't really move it up anymore, but that's good enough. Okay, so if I want to write this over, it's the probability the adult is a male given they have never shopped. Yeah.
So this would be 1,100 instead of 1,000.
Oh, no, because our denominator is female. Thank you for saying that. So whatever's after is going to be the denominator, and then we go in and get the 700. So this would only be if it was switched. Only it would be 1,100 if it was switched. Does that make sense? Kind of? Yeah. Okay. All right. So yeah, whatever's to the right, that's the total we're going to use. So if this was a male that has shopped, that would be my denominator. My numerator would be 400. Yeah. Okay. All right. Okay. Sorry. Sometimes I'm found to miss that. Okay. So never shopped. This is my denominator. Okay. So have not shopped is 900. All right. Since that's my total, I'm now going to go into this column, and my top is either going to be 600 if it's male or 300 if it's female. I want the male, so 600, and that's 0.67. Okay, is that good? The given ones are tricky. Okay, all right, I'm going to scoot it up a little bit. Okay, so B, now we're talking about mutually exclusive events. Okay, so remember, mutually exclusive events, we're going to say yes if they cannot happen together, if you cannot be both. All right, are male and female mutually exclusive events? Yeah. Okay, yeah. All right, what about have shopped and male? Are they mutually? No, I mean, I don't know a lot of men that shop, but technically they scientifically can shop. So it's no, because they can be both, right? Okay, now we want to know, what about the events female and have shopped? Are they independent? Well, I already told you, chances are your answer's no, right? But let's look at why that is, okay? So in order to know if they're independent, we're going to take the probability of the events you see in order. So female, given they have shopped, and see, is that equal to the probability of the first event? The probability that the person's female. That's how you find out if they're independent. And then each side would need to be equal. Okay, so let's find the numbers here just to prove it. Okay, we have a given here. Now my denominator is going to be the total of have shopped. Okay, so I go back up here. The total of have shopped is 1,100. That's my denominator. Okay, now my numerator is I go inside the numbers that made him up and I pick out the female number, which would be 700. I'm going to see, is that equal to the probability of just being a female? All right, well, since this is only one item, what's my denominator? Since it's just one little thing, the grand total, right? When it's just one little item, it's the grand total. And then the total number of females is 1,000. Okay, put those in my calculator. I get 0.7 on the left. I get 0.5 on the right. They aren't equal. So my answer is no. Okay, but that's how you would find it, you know, mathematically. All right. Sound good? Okay. All right, let's flip it over and look at number 4. 4 is tricky. This is a Wiley problem. Okay, got to really use your reading skills here, your skills of deduction. You guys don't read a whole lot. You just skim for numbers and plug stuff in. So you're going to have to really read. Okay, this is tricky. All right, there's a total of 165 doctors in a city. We got that. Okay, of the 165, 70 are female. Of the 165, 23 are pediatricians. Everybody got that? Okay, so there's 165. 70 of this group are female. 25 of that group, 23 are pediatricians. Now it breaks down the 70 a little bit more. Out of the 70 females, 12 of those are pediatricians. Okay, we think we got it? Okay. This wants to know, are the events female and pediatrician independent? Well, we already know the answer. Are they going to be independent? No, nothing's ever independent. But how are we going to find that out? Because what if they want the numbers, and I think they do, from each side? We can't just write no. We're going to actually have to find numbers. Okay, here we go. So we're going to find the probability that the doctor is female given they're a pediatrician. We're going to see, does that equal the probability that the doctor's female? Okay, here's, oh, go ahead. Sorry.
When writing it, do you put whatever you're given first, like female looking first, and then also?
Exactly. Yep. When you're writing this side for the given, it's the events in order. And then when you set it equal to the other side, it's the first event. Yep. That's how you tell independence every time. Good. I was hoping you guys would see that pattern. Okay. This is where it gets tricky. All right. So my denominator for this side is now pediatricians, not female pediatricians, just pediatricians. How many pediatricians are there in the city? 23, right? 23. Okay, good. Now be careful here. Out of those 23 pediatricians, this is where you have to kind of infer some things. Out of the 23 pediatricians, how many of those pediatricians are female? 12. See how that was a little tricky there? Be really careful because students want it to be really explicit and say it, but you kind of have to use, you know, your thinking skills a little bit. Is everybody okay with that? Okay, we want to see, is this equal to just females? So since it's just one item, I need the grand total in the bottom. It's 165. And the grand total of females in the top. There we go. All right, this one, I got 0.522 on one side and I got 0.424 on the other, which is obviously not equal. Okay. Are they mutually exclusive? No. You can be both at the same time. You can be a female and a pediatrician. You can be anything you want, girls, right? Okay. All right, here we go. Number 5. All right, these are really easy questions. They're meant to be easy questions, but students overthink them because you get so bogged down in the formulas. So here you go. We want the joint probability of A and B given they are independent events. Okay, so if you end up, you don't have to, I'm going to tell you the formula, but if you look back at joint probability for independent events, your formula is the probability of A times the probability of B. And this is a great problem because your brain doesn't even have to think because look what they give you. A, probability of A, probability of B. So what are you going to do with these two numbers? You're going to multiply them together. Okay. So I'm just going to take 0.29 times 0.65, and I came up with 0.1885. I don't know why I went out 4 decimal places. Maybe they tell me to in Wiley. I can't remember. All right, for B. All right. Again, tells me they're independent. It's the same formula. All you're going to do is multiply them together. And I came up with 0.0084. Easy enough. Okay. All right, now look at number 6. Okay, so number 6 also wants us to find, hold on, it's not zooming, it's not clearing. There we go. Sometimes my little computer camera doesn't like to focus, and if I stick my finger up in its face, it focuses. Okay, so down here, we also want the joint probability, but it doesn't tell us they're independent. And remember, we talked about the fact that if it doesn't tell us that they're independent, we're going to assume that it's this, right? So it's going to state if it's independent, and we use this. If it doesn't tell us anything, we just have to use this version. Okay, so since it doesn't tell us anything, we have 2 formulas. And I don't even know if I don't even think I gave you the other formula because I felt like it was just bogging you down. But these are both the formulas for joint probability if they're not independent, okay? And it's just kind of the switch of them. That's all. All right, so for this one, all I'm going to do is take 0.36 times 0.87. And I get 0.3132. For this one, I'm just going to take 0.03 times 0.22, and I get 0.0066. And there's my answer. Okay, so based on what was given, I'm using that formula. Based on what was given, I'm using that version. They're the same thing. Okay, it's just two different formulas just based on what information you're provided with, but you're just going to multiply them together. That's it. Joint probability is the multiplication rule. So you're just multiplying stuff. Same thing. All right. Okay. Everybody okay with those? Okay, number 7. Okay, we're not going to overthink number 7. Okay, here we go. We have 2 events. All right, you filed for an application to get a car loan. All right, event A is your loan was approved. Event B, your loan was rejected. What's the joint probability of A and R? Anybody got any ideas? Joint probability means they're happening together. What's the joint probability of both of these events happening together? 0. You can't be accepted and rejected at the same time, right? So it's 0. Why? Because they are mutually exclusive, right? You can't have both happen at the same time. They don't have anything in common. There's no joint commonalities. They're mutually exclusive. All right. Okay, let's look at some more numbers then and practice a little bit. Now, notice we already handled marginal probability. We already handled conditional probability. Now I see probabilities with a little and in the middle. So now we're going to practice joint probabilities, but we're going to do it with a chart. So it's a little different. Okay. All right. First thing you do with a chart is fill it in, right? So let's get some totals. Okay. So there's 255 basketball players that graduated and 76 that didn't. I get 168 males and 163 females. And then horizontal and vertical both gave me a grand total of 331. Okay. All right. So now we're going to look at the probability that they are a basketball player that is female and graduated from college. Okay, so technically, let's look at what that looks like, and then I'm going to give you a shortcut, okay? Technically, that means that we are going to, for joint probability, it's different than independence. I'm going to take the last event that happened, so the probability they graduated, times the probability they are a female given they graduated. That's how you come up with joint probability. So it's the probability of the last event all by itself times the probability of the events in order with a given in the middle. Okay, so I know that's confusing. All right, again, we're going to get to the easy way in just a second. This is kind of the long official way. Okay, so officially, let's find the probability they graduated. Well, it's one item, which means our grand total is going to be in the bottom. Okay, then I want the total of graduates, which happens to be 255. And I'm going to multiply that by my next probability. Okay, my denominator's what's to the right of given. So now I want the total graduates. Okay, that's 255. Then I'm going to go inside and see what two numbers made him up. 126 males or 129 females. I want the 129 females. Okay. I can multiply both of these together in my calculator, and I come up with 0.390. That's my official answer. Okay. The problem is with joint probability, students always forget, and not just students, a lot of people, they forget how to set this up because it's a little strange. Anybody notice anything about these two fractions? Anything they might have in common? Anything you could do to them? Anybody see it? There we go. Look, you can actually cancel those. Happens every time. Then what are we left with? We're left with the big giant total denominator. What's our numerator? It's the item that fits both of those conditions. So if I put my big giant denominator on top, on the bottom, and then I go inside and get super nitpicky and I pick the number that represents females who graduated, look what my numerator is, 129. Guess what that ends up being? 0.390. And you have your answer. So this is what everybody does for joint probability. They do the nitty gritty, down and dirty, fast way. But this is the official, what you're supposed to be learning and why you're learning it way. Okay? Does that kind of make sense? All right, so anybody want to do it the long official way? No, okay, good. Okay, so let's do the next two. Okay, I see an and in the middle, so I know I'm joint. So I'm going to put my big giant denominator in the bottom. Then I'm going to go inside and I'm going to find the number that satisfies both conditions. So I want a number for graduated and did not graduate. Any ideas? Come on, people, look alive. Can't be both, right? You can't get your diploma and not get your diploma. So it's 0. All right, because those are mutually exclusive. Sorry, I was tricking you. I know it's dark. You just had lunch. You don't even know where you are. Okay, there. All right, so you can't have that. It doesn't make any sense. All right, let's do one that does make sense so we can practice. Okay, so I see an and. I know that I'm joint probability, so big giant total is the denominator. Now I want the very specific number that is a male who did not graduate. So male did not graduate. Everybody get 42 for that number? Okay, throw it in the calculator, 0.127. There's your answer. Okay, so joint probability, really easy. Big number in the bottom, really specific number in the top, you're good to go. Okay. All right. Okay. Number 9. All right, so now we are going to have to really put on our thinking caps here. Wiley loves this problem. All right, so 52 employees in an office wear eyeglasses. Okay, so of the 52, 44 of them have single vision correction. So, you know, they can't see far or they can't see close, like they have one issue. 8 of them were bifocals, meaning they can't see either one, right? That's what happens when you get old. You can't see far, you can't see close. Okay, so you got to have part of your lens does one thing and part of your lens does the other. All right. Now we're going to select 2 employees at random. What's the probability that both wear bifocals? Okay, so let's do that problem first. We want the probability that your first one wears bifocals and your second employee wears bifocals. Now, unfortunately, we can't do the quick and dirty way that we did up there. Why can't we do that? Because you're choosing 2 people. So your denominator is going to change for both of these because you're choosing 2 employees. Your denominator is going to change after you choose the first one. Let's think about that here. Okay, so what you're really finding is the probability that the first person wears bifocals times the probability the second person wears bifocals, given the first person also wore bifocals. That's kind of confusing. Not really necessary you write that, but that's what we're dealing with, folks. Okay, here we go. All right, let's find the probability that the first person wears bifocals. Okay, so how many people do I have to choose from? That's my denominator. 52. I got 52 employees. They're all in a room. Okay, I pick one. All right. My numerator is how many people could possibly be chosen, which is 8. Okay, here's where it gets a little weird. Think about this. All right, you've already chosen somebody that has bifocals. Get out of here. They took them to the eye surgeon, whatever, they're going to fix them. Okay, now you're in your room, you're choosing a second person. You still have 52 people in this room? No, because you already chose someone. So how many people are now in the room? 51. This is a really stinky little question Wiley throws in there at you. Okay, 8 people wore bifocals, but you already picked one of them out and sent them off for surgery. How many people do you have left now? 7. So now your number changes 1. Okay, you had to subtract 1 from the top and the bottom given this situation. So you really can only play the quick and dirty game with joint probability when you have a chart and you're choosing one person to satisfy things. Here, we're not choosing one person to satisfy things. We're choosing 2 people, one right after the other. So things change. Okay, now let's try it with single vision. Okay, so if we want to write this again, I'm just going to use S. So single vision and second person also has single vision. This would be the probability that the first person has single vision correction times probability that the second person does, given the first person did too. Okay, if that's confusing, it's not necessary as long as you can plug in the numbers. All right, here we go. So we want the probability that the first person you choose has single vision correction. So 52 people are in the room. Forget the bifocal people, everybody's back. Okay. How many people have the single vision correction? 44. Okay. All right. Now we're looking at the next one. How many people are left in the room for the denominator? 51. And what's our numerator going to be? 43. Okay, 1 less. And that ends up being 0.7134. Okay, good. So just some Wiley questions, but they're a little tricky, so just wanted to go over those. All right, let's see. Jumping on to number 10. Let's see how many we can fit in. I don't think we're going to get all the way through 13, but we're pretty darn close. All right, so here we go again. We're back to our basketball players, but it's different data. Okay, so let's add them all up. Now we have 259 that graduated. We're at a different school. We have 86 that didn't. We have 181 males and 164 females. Our grand total in both directions is now 345. Okay, so we played the basketball graduation game with joint probability, with the and in the middle, right? Now we're going to look at it using or. We're going to look at it using a union, okay? Now, be careful here. There's two ways it could be written. The first one actually uses the word union, okay? Or they might say this, the probability that they are female or did not graduate. Okay, so it would either use the word union or it would actually use the word or in parentheses. I know this has an and out here on the outside, but that's just a weird part of the sentence that also said union. Okay, so remember, joint probability is the multiplication rule. Union of probabilities is the addition rule. So what we're going to have here is the probability that the student's a female plus the probability they did not graduate minus the probability that they're both. So you're going to have three items. There is no quick and dirty way for union. It is the all three fractions, okay? The good news is all three fractions are going to have the same denominator. They're all going to have the big total as the denominator, okay? They're all going to have that. So I'm going to have, I really wrote too big. Okay. So I'm going to have some kind of fraction here, some kind of fraction here, some kind of fraction here. That's what I'm going to have with a union. Three fractions, denominators are always the big giant total. And then I'm just going to grab my tops. So total females, 164. Okay. Total not graduates, 86. All right, this is a joint probability here on the end. We're going to go inside for him. We're going to find the specific number that makes a female not a graduate, 31. Okay, before we find the answer on this, let's talk about it a minute. What we found here, okay, we found the total females. So we found this, we used this column to get this number, right? Then we found the total did nots. We used this column to find this number. Why are we subtracting out 31? Well, look, we counted 31 in the first fraction. Then we counted it again in the second fraction. You have to subtract it out because you counted it twice. Does that make sense? That's why there's always a minus on the union, because you've already used this column for the female. And then you went and used it again for the did not. That's why you have to subtract that number out, because it's already been used twice. So that's kind of help you a little bit. All right. Now, some students will do this the long way and they'll put every one of these in their calculator and, you know, parentheses and everything. But let's think about what we know about algebra. What we know about algebra is if they all have the same denominator, we can just deal with the numerator. 164 plus 86 minus 31 and divide by the denominator once. And we get 0.635. Now you can put every little fraction in and add them all together and subtract. You can absolutely do that. It's just, I find that to be easier. And so I like to share that with you just so that you can see how that works. Okay, and there you go. All right, let's try B real quick. Okay, now we want to find the probability of the union of events. So we know we're doing plus and then a minus, okay, of graduated or male, right? That would be another way it would be written. That's how you would know what you're supposed to be doing. That means we're going to have the probability of the person being a graduate plus the probability they're a male minus the probability they're a graduate and a male, because we will have already counted them twice and we have to subtract one of them out. Okay, so we are going to have 3 fractions. What's the denominator going to be for every single one? 345. 345 for every single one. Okay. Now we're going to look at the total graduates, 259. We're going to add that to the total males, 181. And we're going to subtract out the males who are graduates, 126, because again, we counted that number twice. Does that make sense? Then you can put these in the calculator any way you want to. You can just do the numerators and divide once if you wanted. And I got 0.9101. And there you go. Okay, well, we're only missing 3 problems. I figure there's no reason to have a whole class for 3 problems. So we will do those 3 on Tuesday. I'm confident we can squeeze them in before chapter 5.